Okay, this is the fifth video for IB Astrophysics. We're going to look at how a star changes over its lifetime. In the last video, we looked at the main sequence, red giant, and white dwarf stars, which show up on the Hertzsprung-Russell diagram. Remember, the Hertzsprung-Russell diagram has luminosity on the vertical axis, and spectral class, which is the same thing as temperature, on the horizontal axis. And we need to look at where stars come from. And stars come from clouds of hydrogen gas, and those clouds will collapse under their own gravity. We call those collapsing clouds protostars. Now, as the gas collapses, it heats up. What's happening is it's losing gravitational potential energy, and that gravitational potential energy is turning into thermal energy. And eventually, the temperature of the cloud, at least the center of the cloud, becomes hot enough to initiate nuclear fusion. Remember, that's something on the order of 1 million or so Kelvin. And once nuclear fusion ignites, we now have a star. And specifically, we have a main sequence star. Keep in mind, though, that the cloud starts glowing well before fusion starts. Because, remember, to glow red, its temperature only needs to be about 3,000 kelvins. But to initiate fusion, the temperature has to be at 10 million kelvins. So a protostar can glow even before fusion starts. But once fusion starts, it's now a star. It's somewhere on the main sequence, and it's going to be burning hydrogen in the core. So main sequence stars burn hydrogen in the core. And depending on the mass of the star could have a lifetime of between 1 million and 1 trillion years. You don't need to worry too much about what we call Hayashi tracks, but you should notice that a 9 solar mass star ends up there, 5 solar mass star there, the sun is about in the middle of the main sequence, and very small stars are down in the lower right corner. And main sequence stars are interesting, but not as interesting as what happens when the main sequence star runs out of fuel. And once the core has turned mostly into helium, there's not enough hydrogen there to maintain fusion, fusion basically stops in the core. And what happens is that the pressure drops because there's no energy being produced in the center, so there's less radiation. And what happens is the star begins to shrink a little bit. The result of that shrinking is that the temperature in the core actually goes up. Remember, it's basically adiabatic. Remember, if you compress a gas rapidly, its temperature increases. And eventually, the core becomes hot enough to have helium fusion. Now, helium fusion requires higher temperatures than hydrogen fusion does, around 100 million kelvins instead of 1 million. And typically what happens is it doesn't start slowly. The star collapses, 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 and then all of a sudden helium fusion starts. It's called the helium flash, where the star very quickly becomes brighter and larger, and then we have a red giant. And what happens is this helium flash creates a huge amount of radiation pressure. And that radiation pressure exceeds gravity and results in the star's outer layers expanding a lot, by a factor of 50 to 100. So the sun will eventually, in probably another 10 billion years or so, turn into a red giant, and it will swallow up Mercury and Venus, and probably Earth as well. Even though, this is interesting, the mass of the star actually decreases because a lot of the surface layers just get sloughed off and pushed out far away from the star. Sometimes as much as 40% of the star's mass gets lost that way. The other thing that happens in this process is that the surface temperature decreases. The core temperature is incredibly hot. Remember, helium fusion requires temperatures in the hundreds of millions of kelvins, but the outer layers, which are now much farther from the center, cool off, and the star turns red. And now we have a red giant. Remember, low temperatures, but extremely large radius and therefore very high luminosity. And stars typically spend a relatively short time as red giants. A star like the Sun will spend 10 billion or 10 billion years or so on the main sequence, but it will spend less than 1 billion years as a giant. And that is why there are many more main sequence stars than there are red giants. They're not so much different species of stars as different stages in a star's life, and of course the shorter stage, the red giant, there are fewer stars out there than there are in the longer stage. But then, eventually, the red giant runs out of helium in the core as well. And for relatively small stars, meaning up to 4 or 5 times the mass of the Sun or so, what happens is the star's not big enough to compress to the point that would be necessary to fuse carbon, because helium fuses into carbon. And the mass isn't large enough to raise the temperature enough for carbon for anything heavier than carbon to form. So what happens when fusion stops is that radiation from the core eventually blows away the outer layers of the star to form something called a planetary nebula, which basically looks like a circle around the core of the star. So you've got the core here, and then you've got the outer layers around there. It's not a real violent explosion as stars go, but it produces some pretty cool looking things afterwards for astronomers to look at. Now the core here, remember, was not that long ago undergoing helium fusion, has a temperature of 100 million kelvins. So it's still really, really hot. It'll take some time to cool, but there's no fusion going on. And what that core is a white dwarf. If we look at what happens on the Hertzsprung-Russell diagram, you've got a star starts out here on the main sequence. You don't need to worry about this kink, but basically, when it gets here, this is where helium fusion starts. And then the star gradually increases in luminosity. It's now a giant. And then right here, this is where the planetary nebula forms. And then it cools and fades, and you get a white dwarf. A white dwarf is made mostly of carbon. It's very small and very dense, typically around the same size as Earth. But with a mass somewhere near the mass of the Sun. There's no fusion occurring, but because fusion was somewhat recently occurring, they're very, very hot and therefore appear white. White dwarfs, because there's no fusion, there is no radiation pressure, and what holds them up against gravity is something called electron degeneracy pressure. Basically, in order to get any smaller, you'd have to push the electrons so that their orbits overlap. And because of the Pauli exclusion principle, do you remember that from quantum mechanics? That says electrons don't want to share the same orbits with each other, and so basically the electrons are jostling each other with their elbows, and that's what keeps the star from collapsing under its own gravity. There's something called the Chandrasekhar limit, though. It has a maximum size of a white dwarf, and it turns out the white dwarf cannot be bigger than 1.4 solar masses. If the white dwarf were to be larger than that, then electron degeneracy pressure would not be strong enough to overcome gravity. And in the next video, we'll talk about what happens for stars where the core is bigger than 1.4 solar masses. What you need to know from this video is you need to know that stars form from protostars and how a protostar turns into a main sequence star. What happens to the main sequence star when it runs out of fuel in the core? It turns into a red giant, but you need to explain the details. And then when the red giant runs out of helium, what happens, planetary nebula, and then the white dwarf. The next video will look at what happens when a very large star runs out of fuel. Much more interesting.